Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll take a quick look of efficiency by way of a series of illustrated example problems. This lecture operates under the presumption the viewer has a basic understanding of energy and power and efficiency, as illustrated in the Energy and Power and Efficiency lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. Mastery of efficiency calculations necessitate active participation on your part. As such, I'm asking you to please pause the lecture when asked to do so and attempt the example problems on your own. If your answers don't match those illustrated, feel free to rewind the lecture and correct any mistakes you may have made. Our first problem features a power electronics device known as an inverter. The inverter's task is to take the DC power output of a photovoltaic array and convert it into grid-compliant AC power suitable for export. Let's say the inverter is known to have an efficiency of 96.5%. Let's say the array is setting 3,000 watts or 3 kilowatts of power to the inverter. See if you can determine the usable output of the inverter. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Output is efficiency times input. 3,000 watts times 0.965 yields a usable output of 2,895 watts, or roughly 2.9 kilowatts, meaning 105 watts is directed towards losses, which might take the form of heat or noise. Our next example features a motor with the following nameplate information. At the rated condition, the motor is known to produce 1/4 horsepower of usable mechanical power output and operates at an efficiency of 62%. See if you can determine the required input in units of watts. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. First, we need to convert power output from units of horsepower to units of watts. Given 1 horsepower is equal to 746 watts, a unit conversion demonstrates 1/4 horsepower is equivalent to 186.5 watts. You'll note the nameplate specifies this value in parentheses, where 0.18 kilowatts is roughly equivalent to 186.5 watts. Input is output over efficiency. 186.5 watts over 0.62 yields a required input of roughly 300.8 watts, meaning 114 watts is directed towards losses, which might take the form of heat or vibration. Let's now examine a couple efficiency calculations making use of our previous understanding of power and energy. Let me remind you that energy is power times time. Efficiency affects power. If a device is inefficient, it will waste more power to accomplish the same task, and as a result, it will consume more energy. Conversely, if a device is efficient, it will use less power to accomplish the same task, and as a result, it will consume less energy. Consider a 3.3 kilowatt car charger that takes 8 hours to fully charge a 24 kilowatt hour battery bank for an electric car. See if you can determine the efficiency of the charge process. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Let's first determine the energy consumed by the car charger. Energy is power times time. 3.3 kilowatts of power being expressed for a period of 8 hours demonstrates the car charger uses 26.4 kilowatt hours of energy. The battery pack, however, stores only 24 kilowatt hours of energy. Efficiency is output over input. 24 over 26.4 demonstrates the car charger is roughly 90.9% efficient. Our next problem features a 5 horsepower generator that runs at full capacity for 8 hours a day, and in doing so, consumes 2.5 gallons of gasoline. Let's assume a gallon of gasoline contains 33.4 kilowatt hours of energy. See if you can determine the usable electrical energy output and efficiency of the generator. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Let's first determine the energy consumed by the generator. 2.5 gallons of gasoline represents an input of 2.5 times 33.4 kilowatt hours, or 83.5 kilowatt hours of energy. We first need to convert power in units of horsepower to units of watts. If 1 horsepower is equivalent to 746 watts, 5 horsepower is equivalent to 5 times 746 watts, or 3,730 watts, or more appropriately, roughly 3.7 kilowatts. Energy is power times time. Roughly 3.7 kilowatts times 8 hours yields roughly 29.84 kilowatt hours of energy. Efficiency is output over input. 29.84 kilowatt hours over 83.5 kilowatt hours demonstrates the gasoline-powered generator is approximately 35.7% efficient. Let's take a look at the efficiency of some representative examples of renewable energy systems. Consider an industrial wind turbine with a rotor that spans a diameter of 77 meters. Let's say at the rated wind speed of 12 meters per second, the turbine produces 1.5 megawatts of usable electrical power output. In order to determine the input mechanical power provided by the wind and the efficiency, we're given the following formulas. The area of a circle can be calculated as pi over 4 times the diameter squared. The mechanical power input of a moving column of fluid can be calculated as half times the density of the fluid times the area of the column times the velocity of the fluid cubed. Let's assume the density of the air is 1.225 kilograms per meter cubed. See if you can determine the mechanical power input and the efficiency of this wind turbine. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. First, we need to determine the surface area of a turbine with a diameter of 77 meters. This is commonly known as the rotor swept area. Substituting a diameter of 77 meters into the circular area formula demonstrates this turbine has a rotor swept area of roughly 4,656.6 meters squared. Now we need to determine input mechanical power. Substituting the density of 1.225 kilograms per meter cubed, the area of 4,656.6 meters squared, and the velocity of 12 meters per second into the mechanical power formula demonstrates this turbine is effectively consuming 4,928,572.7 watts, or roughly 4.9 megawatts of mechanical power. Efficiency is output over input. 1.5 megawatts over roughly 4.9 megawatts yields an efficiency of roughly 30.4%. Consider a solar panel with a surface area of 1 meter by 1.5 meters, or 1.5 meters squared. A common performance measurement for solar panels uses something known as standard temperature and conditions, or STC, whereby the solar panel is exposed to light with an intensity of 1,000 watts per meter squared. Let's say at standard temperatures and conditions, or STC, this solar panel produces 200 watts of usable electrical power output. See if you can determine the efficiency of the solar panel. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given the usable surface area of 1.5 meters squared, this solar panel is effectively consuming 1,000 watts per meter squared times 1.5 meters squared, or 1,500 watts at standard temperatures and conditions. Power input to this solar panel is therefore 1,500 watts, or 1.5 kilowatts. Efficiency is output over input. 200 watts over 1,500 watts yields an efficiency rating of roughly 13.3%. Before we move on, take a moment to reflect upon the efficiency ratings of the renewable energy systems. Although I'm not using any specific manufacturer's data, these examples are meant to represent reasonably accurate portrayals of these types of systems. The wind turbine is pretty inefficient, and I'd go so far as saying the efficiency of the PV panel is a total fail. I mean, really, I've seen your lazy lab partner get higher than a 13% on a quiz, so the PV panel is a clear loser. My follow-up to this observation is this: who cares? Renewable energy systems like wind turbines and PV panels use free fuel. Yes, renewable energy systems are initially more expensive to install. And yes, they need to be maintained just like you would maintain a gas generator or a coal-fired power plant. However, unlike a gas generator or a coal-fired power plant, the fuel that powers renewable installations is abundant, inexhaustible, and absolutely free. Not to mention, it doesn't necessitate dirty extraction techniques nor the propping up of a morally questionable dictatorship in a third world country with an expensive military campaign. I think my larger point can be summarized in the following chart. The price of petroleum-based fuel has done nothing but rise. The price of renewables has done nothing but fall.